So welcome to the November Orion Club meeting. Orion is a group that promotes astronomy and science in East Tennessee. And I don't see any visitors to introduce. Well, my wife Janet is a visitor. So tonight we're fortunate to have Lee Riedinger to give us a presentation. And I'm going to ask Ted Barnes to introduce Lee, since he's known him for quite a few years.
Lee Riedinger has had a long career at UT in Oak Ridge. He's a nuclear structure experimentalist, and he's also has, part of his career has been administration. He's been in charge of basically everything at UT, all the research initiatives. He's an APS fellow, AAAS fellow, and of course an experimentalist who's done a lot of work in Argonne, Brookhaven, UC Berkeley, and the Niels Bohr Institute. I remember once when I'd come back from DOE, Lee was giving a physics talk. And I remember Lee stood up and said, he gave a justification that I really like hearing, which was, I'm going to be talking about nuclear structure experiment. The reason is that I really like this stuff. And that's the best possible reason to do physics of a certain kind, is it really jazzes you to work on that area. Since he retired in 2019, just a year after me, he's been working on a number of things, like publications on Oak Ridge and UT and the Manhattan Project, very timely stuff. And he's going to publish a book on this through the UT Press in 2024. And it's the topic of tonight's talk, so this should be very interesting. All right, Lee.
Thank you, Ted. Well, it's great to be here. I appreciate the invitation and see people I haven't seen for a while. Janet Swift was my first human resources officer when I went on leave from UT to be the deputy director of Oak Ridge National Lab in 2000. Did that for 6 years, then went back to the university. And I still feel the same as I said in that talk that Ted heard a long time ago. I just like doing this stuff. I like being around here. I joined the faculty in '71 in physics at UT. You never know where your career is going at that early stage, where you will end up 20 or 30 or 50 years hence. But it turned out this was a great place for me to be at the university, being a nuclear physicist close to Oak Ridge National Lab. And as years went on, I found myself working more and more on the partnership between UT and Oak Ridge National Lab. And that's how I got involved with Ted, in a sense, because he was the first joint person we hired in this collaborating scientist category that we now call joint faculty. And that long time that I've served around here, since '71, and the work I've done in trying to build a partnership is why it behooved me to write this book about the history of the partnership. And that's what I want to tell you something about, covering the 40s and the 50s. And I want to talk a little bit more than I do in the book about Jack Gibbons. Do you know the name Jack Gibbons? Don does. Jack Gibbons, I'll tell you about him. He was a nuclear physicist that came from Duke to work at ORNL, started in nuclear physics, and did seminal experiments at Oak Ridge in the 50s on nucleosynthesis that relates to what you all are interested in. So I want to tell you that story too. So this should be casual. Let me know if you have any comments or questions. Sometimes when I talk in Oak Ridge, people in the audience know more about that topic of history or science than I do, so please contribute. 1940, the status of the university and Oak Ridge. Of course, in 1940, Oak Ridge did not exist. It was a farming community, a set of farming communities, very rural, very isolated. It was self-sufficient farmers. TVA completed 2 dams in the late 30s. First Norris Dam in '36, then Watts Bar in 1939. And then, of course, when the Manhattan Project came along, 3,000 people lived in these farming communities right around here, had to move rapidly. They were given 2 weeks by the federal government to sell their land to the federal government and move elsewhere. And that's 2 weeks. They were given. It certainly wasn't, but the war was on. And so it was a national emergency. In 1940, Oak Ridge did not exist, and UT was not a very good university. James Hopkins was the president of UT through the 30s, and the university did not do very well in the 30s. Those were difficult financial times after the crash of the stock market. The state legislators in Tennessee in the 30s did not really see much of a need for higher education. You know, that was a privileged thing. That's for the rich people, not for the common folk. And so the state did not support university and higher education very well at all. And Hoskins did not do a very good job of convincing them of the importance of higher education. So we had no PhD programs at UT in the 1940. Shocking. So there was little faculty research in 1940. And the story I want to tell in part is that UT needed Oak Ridge to start to exist, needed the partnership with Facilities Oak Ridge in order to progress as a university. Of course, we did have a good football team in 1940. We won the national championship. General Nealon was here, and we were good in football then, still are now sometimes, but we were very good in around 1940. The physics department in 1940 has some important names as part of my story of building the partnership with Oak Ridge. It had Kenneth Hertel. He was the head of the physics department from the mid-30s to the late 50s. And he was one of the few faculty doing research at UT around 1940. Indeed, when sometime in the 30s, the state legislature cut by a factor of 2 the funding to the University of Tennessee. He then realized that maybe the faculty need to do something more relevant to the citizens of Tennessee. So he started research on cotton fibers. Cotton then was a big crop, and he did research on how to improve the cotton crop and did experiments, invented instruments to measure the strength of cotton fibers. So he got the first patent filed at UT and actually helped to start the UT Research Corporation and served as its leader for a long time. Alvin Nielsen was on the faculty in 1940. He came in 1935 at a time when UT had 2,500 students. He rose to be head of the physics department. When I joined the faculty in 71, he had just given up the role of head of the physics department to be dean of the college. Actually, he wore both those hats for 5 years. So the physics building on campus is named after Alvin Nielsen, a wonderful guy, a very good researcher. Kay Way was on the faculty in 1939. She got her bachelor's degree from Columbia, got her PhD at North Carolina, worked for John Wheeler, a prominent nuclear theorist, and she joined the UT faculty in 39. William Pollard was on the faculty in the physics department. He came in 36, actually got his bachelor's degree in 1932 from UT, went off to Rice to get his PhD in physics, and came back to join the faculty in 1936. And that's an important name, of course, in Oak Ridge, in the partnership between the university and Oak Ridge. And Bill Pollard, of course, was ordained as an Episcopal priest in 1954. So he wore a hat, 2 hats throughout much of his career. And of course, a lot of you know the story of what was happening in the late 30s. The neutron was discovered in 1932 by James Chadwick in England. In 1935, Enrico Fermi, the young physicist in Rome, started figuring out how to get a flow of neutrons and hit various targets of every element he could find and see what happens when this newfound neutron would hit a target. Fermi discovered new elements marched up the periodic chart. But his most puzzling result came when he hit uranium with a little beam of neutrons. He found new things, new radioactivities, and he assumed he had made a new element 93 or 94. Uranium is 92. Otto Hahn and Lisa Meitner continued with more sophistication Fermi's experiments in Berlin. And in 1938, they did a lot of experiments of neutrons hitting uranium like Fermi had done. They found 16 new radioactive species. 3 of the things he made with neutrons on uranium precipitated out with barium, and they assumed that they had made new isotopes of radium. But barium and radium are in the same chemical group. But nobody understood that. How on earth, if you hit uranium element 92 with a neutron, how on earth, how do you make radium? That didn't make sense. So they continued those experiments. Fritz Strassmann joined them. He was a very good chemist, a nuclear chemist. And in December of 38, they did the seminal experiment that changed the world. They did some precipitations, found out that it wasn't that you were making radium that had the same chemistry as barium. In fact, you were making barium. People did not understand that. Do you make barium, which is element 56, when you hit uranium element 92 with a one little slow neutron? Niels Bohr didn't understand that. No theorists understood that. Yeah, Ted.
If we could go back to the top line, there's one little wrinkle I discovered when everybody was getting interested in neutrons because of the SNS.
Yes.
If you look into the history, the actual experiment was done by a German experimentalist named Botha, B-O-T-H-E. What Chadwick did was write a little 1-pager or 2-pager saying, I think that new discovery is due to a neutral particle.
Oh.
The real discovery was Botha, but he didn't know what he had.
Well, Botha comes back in another way soon in the story.
Yes.
He worked at Heidelberg.
This is the moderator stuff.
Yes, right. So you made barium. How in hell could you make barium when you hit uranium with a neutron? The world did not understand that. Lisa Meitner had moved. She was the group leader in Berlin, but she was an Austrian Jew. But when Hitler took Austria, she was now a German Jew. So she had to get out of Germany. She went to Stockholm, to Mani Sigbon's, or is it Kai, which is the older one? Kai Sigbon's Institute. And so but she didn't have equipment. Otto Hahn wrote a letter to her just before Christmas of 38 saying, don't understand, it's barium you're making. How on earth could you make barium when you hit uranium with neutrons? She got the letter. Her nephew, Otto Frisch, also an Austrian, now German Jew, was working in England at, he was then in Copenhagen working at the Bohr Institute. Aunt and nephew decided to meet for Christmas of 38 in Göteborg in western Sweden. They were out walking in the snow, and Lisa Meitner showed Otto Frisch the letter, and they sat on a tree stump, literally, and said, how could you make barium from uranium hit by a neutron? Frisch remembered a lecture that Bohr had just given that you could view a large nucleus like uranium as a liquid drop. And then he realized if you took a liquid drop and hit it with a neutron, you might introduce enough energy to get that prolate nucleus oscillating. And the nuclear force is short-ranged. The attractive force, the electrical force, the repulsion of the protons, is long-range. And so you can get to a point in this oscillation where they might split, nuclear fission. And then Otto Frisch did a back of the envelope calculation to realize, my goodness, if that happens, you would get maybe 200 MeV of energy released in that split of that big uranium nucleus. And that's a lot of energy because a chemical reaction involves release of energy. So this is millions of times bigger. Frisch went back to Copenhagen, met with Niels Bohr the day before he was to leave to get on the boat to go to New York to spend a month working with Wheeler, with John Wheeler, later the mentor of Kay Way. And he told Bohr this story, and Bohr sort of said, oh my God, why didn't I think of that? And of course, that was how you were getting barium by hitting uranium with neutron, because barium is about half the mass of uranium when it splits. So on the boat to New York, Bohr worked out the first rudimentary theory of nuclear fission and published that. When they got to New York, Wheeler picked them up in Manhattan off the ship, took him right away to see Einstein. Einstein was excited, and then later on in 1939, he wrote the famous letter to President Roosevelt saying, there's this newfound process, nucleus splits, uranium splits, you get a lot of energy, this could possibly be a weapon, and the Germans are certainly working on it. So that changed the world. By 1941, the physics had been worked out, the experiments had been done, and we understood then the process of nuclear fission. And the absorption of one neutron causes uranium-235 to make uranium-236, and it's unstable, it splits into two. You make fission products, two of them on average, and you get, important thing is they came to realize that you get neutrons, 2 or 3 neutrons emitted in this fission process. Wow, that's what makes a chain reaction possible, because that can cause other adjacent uranium nuclei to fission. So by this time, the world understood. And of course, the British physicists were far ahead of convincing their government that this was something very serious to work on, because the Germans, the Nazis, were certainly working on it. And Heisenberg was leading that effort in Berlin. The US government ignored those pleas from the Brits especially to get involved in uranium research until December of 1941, when Japanese attacked Pearl Harbor. That changed everything. Right after that, Roosevelt authorized the Manhattan Project to see if you could make a weapon out of uranium fission. You all know the history, of course. Fermi had left Italy, presumably he accepted a Nobel Prize in Stockholm. His wife was Jewish, he was not Jewish. He was lucky to get her out of fascist Italy. After he got the Nobel Prize, he came to Columbia, started working on building a pile, understanding fission, moved to Chicago, and in Chicago, he built the first pile of uranium. A lot of uranium, not enriched, of course, a lot of graphite. He realized that graphite would be the moderator. You see those 2 or 3 neutrons from uranium fission are moving too fast to cause other uranium nuclei to fission. You need to slow them down, you need to moderate. That's where Botha comes up. Fermi and Szilard at Columbia did the experiments with pure graphite and realized it does not absorb neutrons, and you could use it as a moderator. So Fermi's pile was a whole bunch of uranium interlaced with graphite. Graphite to moderate the neutrons and cause chain reaction. Botha, the physicist in Heidelberg, didn't have pure graphite. And he concluded that graphite doesn't work, he screwed up. And that's why the Germans went to heavy water as a moderator for their reactor. And that's why that's one reason they took Norway to get to the heavy water plant outside of Oslo. And that's a whole other story. So Fermi succeeded in December of 42 to have a pile, enough uranium, enough graphite. With the Geiger counters, he heard it go critical. He heard the chain reaction start. And he understood that. He had a slide rule out. He let it run for 4 minutes and then said, put in the cadmium rods to absorb neutrons, stop the chain reaction. If you let that go, it would have melted down. There was no moderator, no cooling. They all probably would have died, but Fermi understood that, and so he let it run for 4 minutes to prove that you could make a pile of uranium and graphite and have a chain reaction. The next step was scale that up, add cooling, add shielding, and make a ongoing self-sustaining reactor. And that was Oak Ridge. And the purpose is to breed plutonium-239. It does not exist in nature, but experiments at Berkeley led by Seaborg in the 30s showed that plutonium-239 is a better fission source even than uranium-235. So if you're going to build a bomb, you've got to try, and the Germans are breathing down your neck, you got to try all possibilities, not knowing which will work or not. So that's the purpose of the graphite reactor, is to make plutonium. Very quickly, in September 42, US government purchased, without much grace, 59,000 acres of land in this area. Clinton was a nearby town. Oak Ridge was chosen ostensibly because it was remote. There was a good water supply. And since 36, there was all of a sudden good supply of electricity in the Tennessee Valley. And so it was a good place to build a secret lab. 3 sites, X10, K25, Y12, separated by ridges. You don't know what's going to blow up. You don't want one catastrophe to affect the other 2 plants. Y12, of course, you all know the story. That was successful. The purpose of Y12 was to enrich uranium in mass 235, which is the fissionable isotope. Uranium-235 is only 0.7% of natural uranium. That's in part why the Germans chose to go to build a reactor. They knew they didn't have the energy, technology, supply to separate uranium, enrich it. Didn't know how you're going to do it anyway. But Ernst Lawrence had gotten a Nobel Prize for the invention of the cyclotron, Nobel Prize in 1939. And so he then invented the calutron scheme, a way to use a magnetic field, ionize uranium, bend it through a magnetic field, and you get some slight separation by the charge to mass ratio, which is a little bit different for U-235 chloride versus U-238 chloride. That takes many steps. A whole lot of calutrons were built at Y12. It was a difficult process, a lot of starts and stops. But finally, kilogram quantities of U-235 were produced and taken to Los Alamos for the first bomb. At the same time, work on the graphite reactor was started. That's X10. K25 was built to be a gaseous diffusion plant, a different way to separate uranium, to enrich uranium. It didn't bear fruit immediately, but after the war it did. Y12 was to electromagnetically enrich uranium. X10 was to produce plutonium-239 in the world's first reactor in this building. That worked, that went critical. Lots of problems initially, but it did work. And milligram quantities of plutonium-239 were made in the graphite reactor, and then they figured out how to separate it, milligram quantities of plutonium from the kilogram quantities of U-238 uranium fuel rods, and that was all scaled up quickly for the bigger reactors at Hanford, Washington, which produced the plutonium. By the way, Sam Bell is a name you may hear, important, an early person from UT that was involved in all this. Sam was from Plains, Georgia. His family knew the Carter family. Rosalind just died, by the way, the other day. Sam came to UT to get his engineering degree, finished in 1940, was hired by DuPont, sent to Chicago to work on the reactor project there. Then when it was moved on the theoretical work of how to build a reactor was being done in Chicago, then DuPont moved him to X10. So he worked on the graphite reactor. He stayed at Oak Ridge, started led the reactor division. Alvin Weinberg asked him to start the energy division later on, and he then retired to help his son start the Ruby Tuesday chain. Bill Bugg is one of my co-authors. He and I went to see Sam in 2019 when Sam was 100, and he died recently at 102. So 2 bombs, as we know, were dropped on Japan in August of 1945. The first was the little boy that was a uranium bomb, and uranium from Y-12 dropped on Hiroshima. Then a few days later, the Fat Man, which was a plutonium bomb, plutonium-239, produced at Hanford, Washington. It was dropped on Nagasaki, and finally the Japanese surrendered in August, mid-August of 45. The physics department was, of course, active and impacted by the Manhattan Project. Kenneth Hertel stayed. Funny story, in the early 40s, he was out walking in downtown Knoxville, and he walked past the Andrew Johnson Hotel, still on Gay Street, something else now. He saw 3 people he recognized talking to each other. One was Niels Bohr, one was Arthur Compton, and the other was Harold Urey, 3 Nobel laureates. What were they doing in Knoxville? Well, Hertel didn't know, but he heard whispers about something secret going on in Clinton, and he surmised that these 3 Nobel laureates had something to do with that, and indeed they did. Alvin Nielsen went to Ohio State during World War II. Kay Way went to Chicago, worked in Eugene Wigner's group, trying to figure out how to design a reactor. Pollard went to Columbia to work on gaseous diffusion barriers in the SAM lab. When World War II ended then in August of 45, things happened quickly on the partnership. Hertel already began to think about the fate of Oak Ridge now that the war had just ended. You know, many assumed that Oak Ridge would be closed. The mission had been accomplished. The war had been won. And a lot of people thought that Oak Ridge would be shut down soon after August of 45. Pollard came back to the physics faculty. Kay Way decided to go to Oak Ridge to work after the Manhattan Project ended. Martin Whitaker was the head of Clinton Labs. X10 was called the Clinton Laboratories. He was the head, and he was concerned about how to keep his workforce intact. He wanted to keep Oak Ridge funded. He wanted to keep Clinton Labs funded. But a lot of his researchers had been pulled out of grad school in the Manhattan Project, and they wanted to finish their PhD work. So they were going to go back to wherever they came from. However, if he could get help from UT, maybe they could stay, he could keep them, and they could finish their PhD work at UT. But we had no PhD programs. A real dilemma. So in September of 45, he called a meeting. He attended a meeting with Fred Smith, who was dean of the UT Graduate School, and brought with him the director of the chemistry division to make this plea that we in Oak Ridge need the help of UT. I want to keep my workforce, but I need help in getting them graduate courses, getting them PhDs. And that's kind of where it all started. Already in October of 45, I mean, the Japanese didn't surrender formally until early September, but by October 45, UT Physics Department was offering 2 courses on site at Oak Ridge, answering the plea of Martin Whittaker. Robert Bortz was head of chemical engineering at UT. Kay Way, he hosted a dinner party for Kay Way when she came back from Chicago at the end of the war, and just to reunite old friends. Pollard and Hertel were at the dinner party, but at the dinner party, she said, you know, in Chicago, some universities up here are starting to talk about leveraging the assets of the Met Lab, which would soon be the Argonne National Lab, for their own university research purposes. Why can't you do something like that down here in Tennessee? Well, Pollard resonated on that. And in November, there was a dinner meeting that he organized with Hertel, Pollard, and 6 people from the Clinton Lab staff to talk about that. What could we do to organize a set of universities around Clinton laboratories? And that was followed up by a December 5th conference that Pollard organized, where he had some other universities come to talk about that. A conference on research opportunities in the southeast part of the US, which were pretty primitive at that time. So they needed, these universities felt they needed Oak Ridge to extend to continue. That meeting was successful. The set of universities present, there were 9 universities there. UT and Vanderbilt, Kentucky were the most active and vocal at that December 5th meeting. Whittaker was there. A guy from Monsanto and Carbide and Tennessee Eastman were there to talk about this. And there was a general agreement that the university should unite to try and find a way to leverage the graphite reactor and other facilities at X10 for their research purposes. And they appointed Bill Pollard to be the chair of a committee to see if you can put together this consortium. And 20 universities expressed interest in joining that consortium. That was followed up by a late December meeting held at Oak Ridge High School, where 50 people came to talk about the nuts and bolts of how you might make that association of universities to leverage X10 if it continued to exist. Out of that came the formation of the Oak Ridge Institute of Nuclear Studies, ORINS, and Pollard was the acting chair of that. Kenneth Hertel chaired the Graduate Education Committee, and he took the lead in then expanding the number of courses offered by UT and Oak Ridge. And they started to call that the UT Resident Graduate Program. A bigger slate of courses in physics, chemistry, math, engineering in Oak Ridge for the benefit of people that worked in Oak Ridge but needed to further their graduate education. ORINS formed in October of '46 officially with 14 universities, and Bill Pollard became the director and served in that role until 1974. And of course, ORINS became Oak Ridge Associate Universities in 1966. And so the number of courses offered by the UT Resident Graduate Program expanded each quarter. And by the fall quarter of 1946, there were over 1,000 students involved in taking UT courses in Oak Ridge. 145 are in the graduate program, and Bill Pollard and Robert Bortz were 2 of the instructors. But there was also a component of non-credit courses for the citizens of Oak Ridge, and extension courses, and even high school credit courses for those that did not finish high school. And so this was a way that UT really got involved quite early in Oak Ridge by offering these courses. On campus, chemistry got the first PhD program approved in 1945, physics in 1946. And later in 48, botany and psychology got PhD programs approved. But still, the future of X10, the future of Clinton Labs was clearly in doubt. Robert Oppenheimer chaired a committee that did a report for the Atomic Energy Commission. The AEC was formed in early 47, and Oppenheimer's report cast doubt on whether Oak Ridge Clinton Laboratories X10 would continue. It was poor living conditions, poor lab space, poor management. And Oppenheimer felt that X10, Oak Ridge, would just die. And a month later, a local AEC manager expressed the same skepticism that funding would continue for Clinton Laboratories. And because of that, Isidore Rabi, the esteemed scientist, Nobel laureate from Columbia, came down to try and recruit some of the researchers at X10 to come up to the Northeast and continue their careers. General Groves heard about that. He was not a wilting individual, and he was very quick to stop the raiding of Oak Ridge scientists by Rabi and others. But the formation of ORANS was important for arguing for the continuation of funding of X10, because you had a set of 14 universities that were very interested and were telling their congressmen the importance of funding Clinton Laboratories. There were a lot of changes going on in the mid to late 40s. Congress was wondering about how they should fund, whether and how they should fund Oak Ridge. K25 was clearly going to have a future role, because by 1947, it was clear that electromagnetic separation, Y12, would not be a reasonable way to do uranium enrichment in the future for an emerging reactor industry. Too expensive, too difficult. Gaseous diffusion was going to be the way to separate and enrich uranium in the future, and so K25 had a future. Massive separation enrichment of uranium at Y12 was dead, but Y12 redefined itself to be a laboratory that would have a new mission to make nuclear weapons components. You know, the number of people working at Y12 had declined by 90% by early 47. So it needed a new mission, and the mission was about serving the nuclear weapons emerging industry. Contractors were in flux at the end of Manhattan Project. The Army contracted with Monsanto to operate Clinton Laboratories, X10. Carbide and carbon chemicals, later Union Carbide, was contracted to operate Y12 and K25. The Army got out of the business in Oak Ridge when the Atomic Energy Commission was invented in January of 47. But the future of X10, of Clinton Laboratories, was clearly in doubt. AEC was not happy with Monsanto operating X10, so they then decided to replace Monsanto in May of 47, and a whole year of uncertainty occurred. Oregon National Lab, Brookhaven National Lab were formed in this time period, and they were run by consortia of universities. And so people at X10 were not happy that Monsanto was their manager, or that the next step was not clear. The Orange University said, well, maybe we should do that. Maybe the Oak Ridge Institute of Nuclear Studies should apply to be the manager of Clinton Laboratories. So that was discussed a little bit. Instead, in September 47, the AEC went away from talking about Monsanto or Union Carbide to run X10, and started negotiations with the University of Chicago. But that got complicated because Carbide, Union Carbide was called later, wanted to simplify the union issue in Oak Ridge. There was two sets of unions, one at Y12 and K25, the other at X10, and they wanted to have one managing contractor and one set of union issues. And so what came to be was the Black Christmas of 1947 that had great impact on Oak Ridge. David Lilienthal, who had been director of TVA, was now chair of the Atomic Energy Commission. He announced first that Carbide and Carbon Chemicals would also manage Clinton Laboratories, a company, not the University of Chicago. He also announced that all reactor development programs would be moved to the new Argonne National Lab. Well, this hit Oak Ridge like a ton of lead bricks. You're going to lose jobs. It looked like Clinton Labs would only exist perhaps to make radioisotopes at the graphite reactor and not have a research role. Everybody in Oak Ridge was stunned by this decision. And of course, they complained to the AC and their elected officials. Also, the Orange universities complained a lot about this decision to move all the research out of X10. So already by February then of 48, Lilienthal backtracked and said there is a future for Clinton Laboratories. Then they changed the name to Oak Ridge National Laboratory. He assured that the people that there would be research programs in physics and chemistry and biology, and that Orange would be involved in educational programs at Oak Ridge, and that new facilities would be built. So that seemed like a reprieve. Still, the question of university involvement in the operation of X10 was on the table. The head of the Carnegie Foundation gave a speech in March of 48 saying that, gee whiz, universities should be running Oak Ridge. That'd be great value for the universities to take over management of the Oak Ridge facilities in order, in part, to bolster the inferior research capabilities of universities in the Southeast. Orange was encouraged, as I mentioned before, to compete for the management, but Bill Pollard said, we're not ready. Orange only formed in 46, so by 47, he felt that it was not a robust enough organization to attack managing Clinton Laboratories. Also at that time, Charlie Moak was an atomic physicist at the Van de Graaff in Oak Ridge. He came over to UT to talk to Bill Pollard and say, you really need to do this. We need you to, UT or Orange, to be managed in Oak Ridge. But Pollard said, no, we're just not ready for that. And of course, that debate continued. Finally, Union Carbide did manage the 3 sites in Oak Ridge for 35 years. They decided to back out around 84. We, UT, considered mounting a bid at that point. I was part of that effort then. That's why I had to write this book, because I go back that far. But we decided we weren't ready as a university, and DOE had not decided yet to separate the 3 contracts. And we, UT, did not want to be involved in managing a weapons laboratory, Y12. So we backed out. But by 99, a lot had changed. In 95, DOE split the contracts. ORNL was now a separate contract. And when that topic came up again in 98, we were ready for this. And I was one of the leaders this time again to do what it takes to compete for the management of Oak Ridge National Laboratory. And around Thanksgiving of 98, Bill Bill Madia from Battelle came to UT. Joe Johnson, who just died, was the president of UT, and we all met in Joe's office. And UT Battelle was born that day. We spent 99 writing the proposal, and in 2000, we began management of the laboratory. And that's when I went on leave to be the deputy director. But that's another story. In the late 40s, already then, radioisotopes were being made at the graphite reactor. There were 20,000 shipments of radioisotopes that went out of Oak Ridge from 45 through 1950. There was a traveling roadshow. 5 people from the university and 8 people from Clinton Laboratories went around the state talking about what is nuclear energy, what is radiation, what is the advantage and the risk to the state of Tennessee. We had cattle come to Oak Ridge. The UT AEC Agriculture Research Laboratory was formed on 5,000 acres just out, well, you know where that is. That's where Bethel Valley Road intersects, what road is that? That's Scarborough Road. And so there were 50 cattle that got some radiation dosage when the Trinity explosion occurred, the test in July of 45. That was a test of the first plutonium bomb to see if it was ready to be used to end World War II. The Army had moved the cattle far away, they thought, but still, because of the way the wind was blowing, some of the cattle got some fallout. The farmers were upset because the hair of the cattle, some of it turned gray, and they couldn't sell the cows as they normally would for milk or beef. So they were sent to the UT AEC Agricultural Research Laboratory. And so they followed then the cows. They did research on studying the effects of radiation on living species on cows. Turned out that their hair came back. There were many generations of cows born after that. None of them had any radiation damage or bad effects from the fallout. So it was a successful experiment and new opportunities for UT faculty and grad students to work on ag-related research relative to radiation. Also, nuclear medicine was born at this agricultural forum at the yeah.
Did they specifically look for strontium-90?
Yeah.
Okay, good.
I think so. Yep. And you know, the NIH in Bethesda, Maryland had some ideas of using gallium-72 with a 14-hour half-life to whether it would go to bones in mammals and could seek out tumors in bones. But they didn't have access to a reactor there, so they moved that here to the UT Agricultural Research Lab because the graphite reactor was nearby. And there you made gallium-72. They injected it into a pig and then studied the pig, killed the pig, studied it, and found out that indeed gallium does concentrate in bones. And that was the beginning of nuclear medicine that then advanced greatly in subsequent decades. And at the same time, in the late 40s, Eugene Wigner was here, came from Chicago, came from Princeton, and he and Weinberg started reactor programs. You see, the graphite reactor was the first reactor, but it was air-cooled. If you wanted to make reactors for naval ships to make power, air cooling was just too inefficient. And so they did the experiments to realize that water cooling would work. So, you know, Wigner was a Hungarian Jew that came from Germany, came to Princeton in 1930, and he led the team at the University of Chicago, the metallurgical lab during the Manhattan Project. And when he moved to Oak Ridge in 45, he brought with him Kay Way and Alvin Weinberg. Weinberg got his PhD at the University of Chicago in mathematical biophysics, but went to work in Wigner's group at Chicago, and then came with Wigner to Oak Ridge. And of course, Weinberg then, that he's the greatest Oak Ridger in my view. He was lab director for over 20 years. So they started a very important reactor research program. And in the 50s, 9 different nuclear reactors were developed under the leadership of Alvin Weinberg, the laboratory director. The impact of all that development on UT was very profound. Nuclear associated courses at the university in physics and chemistry and even economics and sociology occurred based upon this ongoing presence of nuclear experts in Oak Ridge. We got our first PhD programs. The number of grad students increased greatly. More faculty research and access to radioisotopes for research in different areas. And even in 1951, Brame was the president of UT, and in the Oak Ridge O&L Laboratory News, June of 51, there was his quote that could have been written last week by Randy Boyd, the current president. The message is the same, that university has been strengthened as a research center, as a training ground for young scientists because of Oak Ridge. So already in 51, it was clear that the university was benefiting greatly by its partnership with Oak Ridge. Indeed, in 1951, 29 UT faculty were consultants at X10, Y12, or K25. And I've circled in red the physics department faculty, all of whom I knew when I joined. They were still around. And then there's a young engineering faculty, Bill Snyder, who became dean of engineering and later chancellor of the university. He used to play the organ at the Tennessee Theater. So that's the beginning of what TED became in 1989, the beginning of the shared faculty business, where 51 or 29 faculty served as consultants. Of course, there was a fence around Oak Ridge until March of 49. That came down finally. The shopping center in Oak Ridge was built in 55. In 58, 3,200 homes previously owned by the Army were sold to residents. Oak Ridge Incorporated in 59. There was even consideration of building a college in Oak Ridge at that time. Howard Baker Sr. was a respected Tennessee congressman to the US House. He suggested in 57 that there be a community college on this land right here. UT considered a campus in Oak Ridge, but that didn't work. Floyd Kohler chaired a committee to think about starting the College of Oak Ridge. And 1,000 people in Oak Ridge gave some money, so $100,000 was raised. About a year ago, I gave an Oracle course on this topic, and 3 people in the audience said, I gave money to that in 1961. So with that money, they hired a president. Sumner Hayward was his name. He came in, I think, 62, but he only stayed for 9 months, and then he went elsewhere. And when Hayward left, then the idea of a College of Oak Ridge died. And then nothing happened until Roane State campus was erected here in 1999. was an idea went back all the way to 57. Of course, there was a decade of reactor development in the 50s. Even though AEC wanted to move reactor programs to Argonne, Argonne was not really ready to accept all of that and take the lead on that. But Alvin Weinberg managed to keep some reactor programs at Oak Ridge, and they grew greatly in the 50s. 9 different kinds of reactors, 3 different swimming pool reactors. The tower shielding facility, you can still see those erections there when you go down I-40. That was part of the aircraft reactor experiment. That was the biggest program funding Oak Ridge National Lab until 61. That was the idea that let's build an airplane with a reactor as a power source. You want to be able to have an airplane fly without refueling for 12,000 miles so that you could drop bombs on a distant enemy. And so that was over a decade, a big program here. And the purpose of the tower shielding facility was to suspend a reactor and then suspend different shielding, because the problem was to have shielding light enough, shielding around a reactor to heavy enough to protect the pilots, but light enough that you could get the aircraft off the ground. And so a decade of research was done here. But then, ICBMs were invented, and then that meant that you didn't need a nuclear aircraft as a weapon.
I think Carter killed the nuclear aircraft thing.
Oh, no, it was before Carter.
Okay.
It was killed in 61. Carter killed reprocessing. The US should be reprocessing our spent fuel rods that we take out of reactors, but Jimmy Carter killed that. Well, the centrifuge program was killed under Reagan. That was 83. So there have been various people that had impact on Oak Ridge nuclear programs. Out of this great emphasis on reactor development at Oak Ridge in the 50s came the nuclear engineering department at UT. Pete Pasqua organized that department in 57 and served as the first nuclear engineering department head until he retired in 88. There was a building, a former power plant in back of the hill, that had his name on, the Pasqua Nuclear Engineering Department. But progress goes on, and so that's been torn down in the last 5 years, and a big, new, beautiful nuclear engineering building has been constructed called the Xena Engineering Complex. But still, the Nuclear Engineering Department, UT, is highly respected. It's one of the top departments of nuclear engineering in the country. And that really only happened because UT is next to Oak Ridge. Nuclear reactors, nuclear energy, of course, has decreased in the US a lot. We used to have 103 power reactors putting electricity on the grid. Now we're down to 93. That's going to decrease by a factor of 2 in the next 20 years as operating licenses expire because the reactors are old. So now we're down to, in 2022, 18% of our electricity in the US came from nuclear. Of course, the number for coal has dropped by a factor of 2 in the last 10 years. The US will never build a new coal burning power plant, in my estimation. The number here for generation of electricity by natural gas has doubled in the last 10, 15 years. And these numbers are slowly creeping up. But they're not big enough to supplant these two things. And so we need nuclear. We all know that in Oak Ridge. That's a steady form of electricity generation, runs like a clock, and it's starting to come back. So in Oak Ridge, even TVA intends to build a small modular reactor on the former Clinch River breeder reactor site. Kairos Power is planning to build Hermes, a test pebble bed reactor. Two companies are forming here to make pellets. A pebble bed reactor is helium cooled, and it's little pebbles filled with many kernels of uranium oxide, covered with 3 layers of alloys. The idea being that fission products can never escape, even if you melt the core, even at a very high temperature. So you'll never have a release of fission products. And so that's a future direction for nuclear power. Many people have gotten their PhDs, prominent people, but and there's been a lot of advance in the partnership with UT. But I want to talk for a few minutes about Jack Gibbons, who I think highly of. Jack joined the physics division staff in '54 after his PhD in nuclear physics at Duke. And he started working with Dick Macklin, another big time name in the history of nuclear physics in Oak Ridge. And together they started using protons, pulse protons from the small Van de Graaff reactor in the physics division to make neutrons, low energy neutrons that would be important in stellar processes to make elements, nucleosynthesis. And these are very important measurements that Jack and Dick Macklin did in the 50s and 60s. So Alvin Weinberg, Eugene Wigner, Art Snell were people that hatched this idea to start to build linear accelerator expertise in Oak Ridge. And so they got the first Van de Graaff, a low energy Van de Graaff, around 1950. Of course, now we have bigger Van de Graaffs. This is now shut down, but Van de Graaffs at Oak Ridge grew to be not 2 MeV, but 25 million volts. That was the Hollowfield accelerator, the vertical folded accelerator that has now been defunded. And so that's been a strength of Oak Ridge over many years. But the importance of what Jack Gibbons did was to sort out how stars make elements. There's the R process, the rapid neutron capture process. Well, of course, the lightest elements are made in the Big Bang, hydrogen and helium, 13.7 billion years ago. But when stars explode, for example, supernova, you have a very rapid process of making elements far from the line of stability, capture a neutron, make the next isotope, the beta decays to the next element, and you work your way all the way up in this rapid neutron capture process. But in some stars like red giants, it's the slow neutron capture process, the S process, that dominates along closer to the line of stability. But people then were trying to understand these two processes. And some elements, helium and hydrogen are made in the Big Bang. But tin, for example, is made partially, the calculation showed, in supernovae, that's the blue, that's the R process, and more slowly in red giants, the S process. But then trying to sort out which is which was a challenge. And Jack Gibbons did a lot of important experiments. So he did neutron capture measurements of the cross sections in isotopes of samarium and tin. And that's important because in tin, for example, these are the stable isotopes of tin. You capture a neutron, you make the next isotope. This can then beta decay. But you see, this one you can never make by the S process. So some of these you can make by the R process and some by the S process. Slow process. You know, if you run into a stable isotope when you capture this neutron, then you can't beta decay to this isotope of tin because that's stable. And so you can't make that in the R process. So Gibbons' experiments focused on samarium, measuring neutron capture cross sections in two isotopes of samarium, 148 and 150, that cannot be produced in the R process because the precursors are stable. They measured those cross sections, published that in Nature, the journal Nature, in '63, and what they measured was in line with the predictions, the theoretical predictions of what the S process should do that came out of the work of Willie Fowler and his colleagues in 1957. So Jack Gibbons and Dick Macklin did very important measurements here about nucleosynthesis. In 1969, Alvin Weinberg asked Jack to start an environmental program at the laboratory because reactor programs were dying, research programs. The aircraft nuclear program died in '61. A lot of concern about safety of nuclear reactors by the late '60s. O&O was changing, and he asked Jack to start working on environmental programs. And so Jack Gibbons started a number of energy efficiency and energy generation programs at the lab. He went to Washington in '73, be the first director of the Federal Office of Energy Conservation. You know, that's the OPEC oil embargo that promoted all of these changes in the US government. He came back to Tennessee in '75 and he started UT's Energy, Environment, and Resources Center. Went back to Washington in '79 to be the leader of the Office of Technology Assessment, which was then not independent, nonpartisan office to advise the Congress on complicated issues of science and technology. Well, they decided they didn't need that, and so they abolished that 20 years ago or more. And then Jack served as Bill Clinton's science advisor from '93 to '98. So he's a wonderful example of a person who started here, served both the UT and the Oak Ridge programs, helped build a partnership, and he's just one of many who have contributed to this partnership that has lasted 80 years between the university and the National Laboratory. That's what we write about. That's the book. My co-authors are Al Akabus and Ray Smith and Bill Bugg. That book has gone, we've been writing it for 4 years, almost 5. So it's finally getting close. Al Akabus is not here, but he's worked a lot on this. I think he's listening on Zoom tonight. And so that should be done finally along about mid-2024. And that will have been 5 years after I wrote the first sentence. So eventually you will see this in press. Okay, that's the end of my story. Thanks for listening. And any questions, please?
Question, Dave.
Yes.
Got 2 thumbs up from Al.
Oh, okay, good.
My question is concerns with Fermi pile. Maybe it's a little off topic, but I'm always curious about all these luminaries sitting there getting exposed to neutrons. The question is, what was their dose, and why did the Germans not go in that direction?
No one knew how to measure a dose then. So no deaths occurred, no report of serious illness or anything. It only ran for 4 minutes, so it's a very minimal dose. So that does not seem to be a problem. The Germans felt that they made that mistake, Botha and Heidelberg, that graphite moderation would not work. So they went to heavy water. And they didn't have any heavy water supply in Germany, and they tried to get it from Norway, but the Norwegian resistance sabotaged that shipment of heavy water to Germany, sank that boat. There's a movie about all this. What's it called? Kirk Douglas plays a Norwegian chemist in this movie. Yes.
The German general brought up the point that, like most governments, they built 2 plants, one in Sweden and one in Germany. They had a backup plan. We got there first.
Yeah. And when we got into Germany after they surrendered in spring of 45, we found the site of the reactor program, and they didn't get to first base. And that was maybe in part because Hitler didn't give the resources. Now, Werner Heisenberg claimed till the day he died that he slowed down the German project. But nobody believes him. Nobody beyond, you should see the movie or the play Copenhagen. That's about this famous meeting of when Heisenberg went to see his former mentor, Niels Bohr, in occupied Denmark to talk about things in a very awkward situation. And that meeting crashed and burned, and Bohr and Heisenberg never spoke again and never agreed on why it crashed and burned. Bohr said that Heisenberg was trying to pump him for details on the Allied Manhattan Project. Heisenberg said he was trying to signal to Bohr that he would slow down the German effort if Bohr could get the Allies to slow down. So no one knows. Ted.
Probably most of us here have read a great deal about the period and everything that went into the history of developing the atomic bomb. Occasionally we were lucky by random irrelevant things. Like the Nazis, from what I've read, Hitler especially, really didn't like nuclear physics because it had a lot of Jewish.
Sure.
He called it Judaphysik.
It was Jewish physics. Yes.
And so he wasn't really interested in supporting it.
That's right.
And another problem was the German army of research projects, military development, had a rule that they wouldn't fund any project that would take more than 9 months to produce a weapon.
Okay.
So this was too far in the future.
Yeah.
Many smart people went into the ovens. Yeah.
Yes.
Did I understand you to say that the Calutron process produced essentially all of the uranium used in Limbo?
Yes.
But then the gaseous reactor, so that was not efficient for...
It wasn't mature enough. Inventing the barrier for the gaseous diffusion project where different size uranium hexafluoride can migrate through, depending on whether it's 235 or 238 uranium, that took more time. It didn't bear fruit during the Manhattan Project, but a few years later, it was ready to go. Oh yeah, well, much cheaper. I mean, the calutrons used a lot of electricity. And so as a commercial enterprise, it didn't make sense. Gaseous diffusion was much cheaper. And of course, that was the answer until '83. Long time. Down.
The fission reaction, emits the neutrons with a slight delay in time. And as I understand, the people that originally, the original Chicago pile, they didn't realize that there was this delay in the neutrons coming out from the reaction, and that if there hadn't have been the delay, it would have been much harder to control the chain reaction. I'm just wondering, when did they figure out there was this issue, the delayed neutrons? It was sometime after Chicago, I presume.
Well, I don't know. I don't view there as a delay in the neutrons emitted. Now, there is an issue with spontaneous fission of plutonium
Yeah, there's.
240.
No, I know. I mean, in nuclear engineering, this is one of the early things I remember learning was there was these different groups that have different delay times.
Huh.
It makes a big difference on how controllable a fission reactor is. If there weren't a delay, it would be much harder to do. The thing would exponentiate much faster.
Yeah, well, I'm not really aware of that.
But it's more technical.
Okay. Huh. Do you know about that, Ted?
No, I hadn't heard about that. But I wonder if you might be thinking about some.
Ted, could you speak up for the,
It's right, it's the fission reactor itself.
I hadn't heard about it.
I could look up.
Dr. Riedinger, this is
Yeah.
Roger Macklin.
Roger Macklin.
Yes, indeed. I enjoyed your talk. I would mention that my dad, Dick, was lead author on most of the nucleosynthesis and cross-section measurement papers. But I wanted to ask you about the viability of molten salt reactor with the thorium cycle. Do you have any
Well, sure.
ideas concerning that?
Well, that's what Alvin Weinberg believed in. That's what Alvin wanted to build. And he ran the molten salt program with AEC support. But that's one thing that got him fired in '72, was his insistence that light water breeder reactors was not the way to go, and that a thermal breeder reactor based upon thorium was the way to go. That's the molten salt reactor. And he just objected a little too much. Milton Shaw finally got him fired. So that's coming back now, Roger.
That was
There was
my understanding.
a conference at ORNL in the last year about the future of molten salt reactors. So the idea is resurfacing.
Excellent. Thank you.
And Roger, it was good to see you a couple weeks ago.
Yeah, sorry you can't see me now.
Your father was a legend.
Okay, are there any other questions? Well, if not, we have a gift we would like to present to you. This is the highly sought after and very unique Ornell coffee mug, Orion coffee mug.
Well, that's very clever. Now, who designed this?
It's got the Orion constellation on it there.
Yeah.
Did you get it?
Thank you, Donnie. That's really cool.
Well, thank you again, Lee. That was really quite interesting and very good seminar for us. Next, as I've told several of you, I have recently gotten a new telescope. So this is the C-Star S50 made by ZWO, which makes a lot of cameras, and it comes with a little carbon fiber tripod. And it just screws on top of that. I'm not really going to do much with it, but I will turn it on here. So I've had it about a week and a half, and these are some of the pictures I've taken with it so far. Fortunately, we did have some clear weather here. It's 1980 by 1100 or something.
Does it track?
Yeah, it's so it's an alt-azimuth type of system. So it's a 50 millimeter lens, and you just control it from the phone. And really all you have to do to get it started is to get it level, and then you have to calibrate the compass, which just involves picking up and turning it around a few times. And then once you get that done, you just tell it what you want to go take a picture of, and it goes and finds it. It may do some plate solving to make sure it's pointing in the right direction, but it gets, yeah, and it gets these things centered. I mean, they're very nicely centered. The main difference is that it's all, it's a portrait mode picture that it comes up with, which I suppose it's because it would fit nicely on a phone display, but you can crop it down as I've done on some of these. And it has a little solar filter, so I can take pictures of the sun with it during the daytime.
So you're using digital zoom? Does a 50mm eyepiece won't pick up the sun that big?
Well, again, I've cropped it down. It was a smaller image in the original picture. Yeah, and then these are some other things I've done: the moon and Horsehead Nebula.
You got the whole set on that thing?
Yeah. I mean, it took about an hour of exposure. What it does is it takes 10-second photos, and then it stacks those together. And so you just set it up, get it started running, and then you can go doing something else and come back to it. So they suggest not doing much more than an hour of total exposure, because since it's all azimuth mount, it does have this the field rotation. That is, it will keep centered. It'll keep whatever you're asking it to look at centered in the middle of the image, but when it goes too far, the stars around that begin rotating around the center, and so you start having trouble stacking if you get too much of that. It's really a nice, high-quality little optics system. So here I'm comparing it with my Celestron. So the whole system you usually see me using out at Tau weighs about 60 pounds, probably costs around $5,000. Takes me maybe 45 minutes to set up and get aligned and everything. This thing is like 6.5 pounds. I can pick it up easily with one hand. The ones now cost $500. This one cost me $400 because I was one of the early adopters for it. And I would say it takes maybe 5 minutes to set it up and get it aimed at something. And so it's like a factor of 10 difference in cost, factor of 10 in weight, So it has this attraction. It has a triple apochromatic refractor in it. It's a Sony CMOS sensor, 1920 by 1080, 50mm aperture, 250mm focal length, and it's f5.
You can get that kind of sharpness with 2 megapixels.
Yeah.
Is the Celestron better still?
Well, that's what I'm going to. In order to not make my Celestron feel bad, I have made some comparisons here. So here's M31, the Andromeda Galaxy. So you can see I get a lot more detail with the bigger system. Here's M33, the Triangulum Galaxy. Again, it's it's a little blurry here compared to that. So it's.
What did you process with it?
I used PixInsight. I did do processing on this with PixInsight, so I did some work on it, but it still comes out looking pretty good even without that. I should have included the ones without processing. And here's the Pleiades. Again, you get more of this wispy structure in the clouds around the stars than you do over here. So it depends how big of a hurry you are and what you're looking for and then it has a scenic mode, which I didn't make a picture of anything here, but there's a guy that posted on Facebook. He was in South Padre Island here at the upper right-hand picture showing where his sea star is and where that rocket, the Starship launch was. And he posted a video of the Starship launch, which was actually, it was quite clear and well defined. I mean, so, you know, you can also use it for scenery things, but of course he couldn't, the thing doesn't move fast enough to keep up with the rocket. So he just got the kind of the initial lift off of the rocket, but it does have that capability. So that's basically what I had to show about this, and maybe I'll have more to say in the future about it.
So is it telling you when it says, uh-oh, you've just chosen the horse head, this is gonna take you a while, we're gonna do it for an hour. And if it doesn't work, we're gonna use a built-in photo. Does it tell you?
No. No, it doesn't tell you whether it's going to work. It just goes ahead and starts stacking, and you have to be the judge of that yourself. So it does live stacking. So.
Okay, ladies and gentlemen, Lee, I should explain this. This is my kitty cat. When I started making this, I thought these series, everybody loves pictures of cats. So I'll just lead off with a picture of the cat. And that became a routine. So this is the 9th such big kitty presentation, roughly one per month. Note she has stars in her eyes in this one. And that star, I'll tell you more about. Her name is Franny, by the way. She's a really cute kitty. Now, this is about the occultation of star TYC 4687-0122-1, which is there to the right. It's 9.5 magnitude, which is below your best binoculars, just by a little ways. It's 20 or 30 times fainter than the naked eye can see under ideal conditions. And it was occulted recently by asteroid 785 Swatana, which is about 100 times fainter than the star. Now, I did have one correction, Don, for your little slide. It said I was going to be talking about meteor occultations. Nope, that's too hard. This is an asteroid occultation. So there's a star out there, a meteor drifting along, and the Earth going around the sun rather faster than the asteroid is drifting along. Oh no, I've got it now. And so you got to get it all lining up just right, with any luck, to actually catch the star going out. Whoa, that's one hell of a game of billiards. And this was done successfully, although at the time we thought we'd all failed, me and everybody else who was looking at it, at the star. So this was done at Tau, 2:43 a.m., the 22nd of October, 2023. Yay, all right, we did it. It's Tau's first observed occultation. The organization that keeps track of occultation measurements is quite happy with us and looks forward to future events. I hope they're successful as well. So I won't go through this because I'm pretty short on time, but you might wonder, how often does this happen? This either must happen all the time or almost never. Well, if you plug in some numbers, like we know about 1 million main belt asteroids pretty well, we know their orbits. You go down to 12th magnitude stars, which is about the limit of where it's easy to do this. There are 10 million of those. So I'd never thought of this before. With all those stars and all those asteroids, there are about 10 to the 13th asteroid shadows piercing the solar system, looking for a planet. Okay, now how many of those 10 to the 13 shadows actually hit the Earth? Rough estimate, 2 AU circular disk for the size of the asteroid belt. This is a hand-waving order of magnitude estimate. The ratio of the Earth's facial area to that disk is 10 to the minus 10. So you'd estimate about 10 to the third of those shadows at any one moment actually hit the Earth. Now, of those, what's the chance it's going to run over where you are? Well, you know, it cuts across a band across the Earth's face. And it's the size of that relative to the whole Earth is about the size of an asteroid relative to the Earth, 10 to the minus 3. So you end up with about one shadow per given set, you know, at a given moment that's going to hit where you are. At any one moment, you probably got a shadow to within these, if you know where to look, which you don't. Now, the transit time to switch from one batch of tracks across the Earth to the next one, to the next one, time for the shadow to go, is ballpark 30 minutes. So in one night per observing, my order of magnitude estimate is you might see 10 occultations using a 12th magnitude star, or, you know, or brighter. If you look at the predictions of the organization that measures these occultations, IOTA, they have continually running computers that spit out interesting places where an occultation is taking place, especially given your location, you know, ones where you're in the shadow. And for here, it's about 1/10 of an occultation per night. Now, I've asked the real experts I've gotten to know, how many are there per night? And the best number I've gotten is, oh, quite a few. You know, I've started to realize they haven't actually plugged in this back of the envelope calculation. So somewhere in there, you'll usually find one maybe per night, maybe 2 or 3 if you do a better job. Now, what do you need? Oh, so that's the organization IOTA, which of course spells out occultation and timing and things like that. It was founded in 1983, and I just joined recently, because I thought this would be a very fun thing to try at TAL. So here's an example. This is that very event, 785 Zoetana, blocking out star TYC 4687-01288-1 at 6:43 Universal Time, or 2:43 Eastern Time, AM, 22nd of October. So there's the shadow track across the Earth. Starts at upper right and goes to lower left. You can see it looks like Tennessee might be favored by this. Well, maybe. It tells you interesting things like the maximum duration of this eclipse. Far upper right, 3 seconds. So you can't fall asleep. You got to pay attention. Be ready to catch this. So that's where the the real technical work was, setting up something that would catch it. Now, when you zoom in on that path, you see that really is a special occultation. Where the telescope icon is, that's tau. The green line is the center of the shadow. The edges are the 2 blue lines. And then the other stuff, the red ones, are uncertainty, the thing. So tau was essentially right at the center of this particular occultation by this 50-kilometer wide asteroid. Looks very, very lucky, but because I'd gotten to know how their programs work and installed them on my own computer, I could continually look for things that might be interesting for us. So I knew about this one, you know, several weeks in advance, and was practicing on stars of about the same brightness. Now, the other good thing about this one, for a first attempt, was, first there's in the sky where it took place, was predicted to take place. If you're an astronomer, that's Cetus, the sea monster down there, and that's Pisces up above. And there it says 785 Zoetana, and it's kind of fun to run your the SkyX program and gradually crank up the time. You see, that's 2:43:05 AM, the 22nd of October. As you crank it up an hour at a time, you can see the asteroid boop, 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 working its way over. And then you can see this very exciting moment when there's a white star disk with a little purple asteroid disk inside it. So that's when you're trying to catch it. Now, here's the region in question. And there's the star. Of course, amateur astronomers like us learn that you store the star field in your mind. So when you're looking through whatever setup you've got, you want to recognize the star field, get so it's familiar. There's a smile of 3 stars. The one on the right is the guy we're after, to see if it goes out. Those are all about 9th or 10th magnitude. And then you get to the left and you do a hook up, over, and come back down through those 2. So watch for 3 stars and then up and over like that. Now here we are waiting for it to be 2:43 AM. Much to my surprise, my missus came along for this. I was stunned. I mean, normally she says, okay, you go have fun. But she thought this would be an interesting thing. So here we are waiting for it. The first 3 or 4 hours was kind of slow, but then as we got within 2 hours and then 1 hour, it got more and more and more exciting. Between midnight and 2 in the morning, this damn cloud appeared. A long watermelon patterned stratusy kind of thing that just got bigger and had haze around it and very slowly moved along. This is looking to the south. Well, the telescope's looking to the south. And people were coming over and saying, sorry, Ted, it was fun. We'll have to try this again later. But then about 2:15 or so, the sky started clearing. A miracle happened. We got the miracle we wanted. The sky pretty much cleared off by 2:30. And I realized we were in business. And it got to be a lot of fun. DR and Larry were both at their telescopes, and they were looking for it. So to help them out, I started doing a very theatrical countdown. 8 minutes to go. Every few minutes, 6 minutes to go. 4 minutes to go. And it was a lot of fun. But then it got to be 2 minutes, and I was starting to get a little shaky because there's a lot of things going on. We're watching it on our screen here. That's my SharpCap setup screen. There's Agatha at my left, OTA pointing up at the right region. So we're watching the stars on the screen, and we can actually see this 9.5 magnitude star as a faint little dot near the middle of the screen. So we're going to watch it go out. But I've got something else set up. I hit a certain button on SharpCap, and it begins rapid captures. And I've set it to, after button press, capture 200 exposures of 0.1 second each. Because some tests had shown that I could pretty much make out a 10th magnitude star at full gain for the camera, even with only 100 millisecond exposure. So that was the idea. I would capture a whole lot of individual frames, and I could see if the star went out and when it went out. So I'd be able to turn in a start time and end time, and better yet, a duration. Is it really 3 seconds with a plus or minus 0.1 second accuracy? If this all worked, cross a lot of fingers. I was thinking 50-50. Agatha was certain it was going to work because we had all this equipment set up, but she's not skeptical enough. She hasn't come to enough meetings. Oh, and this is Alan Poole, who snuck up behind us and took this really cool picture. So here's frame number 1. When it got to be 7 seconds, and I hit the start button, and it's capturing a 10th of a frame, a 10th of a second frame continuously for 200 frames. So remember the smile of 3 stars? There it is. And the hook up, over, and down, those 2 brighter ones. So here's our target star, right there. And the predicted time, oh, that's okay. Predicted time of the occultation is October 22nd, 2023. See that little fudgy stuff up there? If you blow it up, it's printing out that same information there for that frame. Predicted occultation time is universal time 6:43:04, maximum duration 3 seconds. And this first frame was actually taken at 6:43:00, so 4 seconds to go before it should go out. There was an estimated uncertainty in the prediction of 1 second. So let's go, that's frame 1. Oh, and there's the frame center. So I've done a pretty careful job of aligning on background stars, getting set up for this. I actually used 12 stars. This is where you point the telescope and record a star location in your crosshairs. By the time you got 12, you got a pretty good map of the sky. So by telling it to go to the coordinates of that star, I wasn't too far out. All right, so we'll continue now, I think. Oh, yeah, there it is. For what it's worth, it's quite a ways out there. It's half a kiloparsec away, F5 spectroscopically. All right, so back to the frames. It's still on. That's frame number 22. Nothing's happened to it. Of course, I wasn't seeing this. The rest of us, DR and Larry were watching, just staring through their eyepieces. We were watching the little white dot on the screen as the time approached. They didn't go out. They didn't see it go out. It didn't go out on our screen. It was a failure. We got up to 20 seconds, 30 seconds, nothing. It was still on. So everybody said, sorry, Ted, it was fun. Didn't work out this time. Had no idea what went wrong. And so we shut everything down, got home at 4:30 in the morning. Of course, I couldn't sleep, so I pulled the record of these images out of my computer and clicked through them one at a time to see if there was any indication of what went wrong. So this is frame number 22. Frame number 23. See, we're iterating through them at the upper right. Oops. Frame number 24. It's weak. Now this is going to go out just like that. So if you're integrating over 1/10 of a second, when it actually goes out, you're going to have a frame in which it's gotten some light, but not the full dose. So that's why that one is weak, perhaps. Go to the next frame. It's gone. Star is being eclipsed by the asteroid. So let's see how much further we get to go before it comes back. We hope it comes back. It's supposed to be 3 seconds, so this is just when it's starting. It says 2.7 seconds roughly. Frame 26 out. Frame 40, it's still out. So this is about 1.7 seconds into the occultation. 41, 42, it's back. That's actually 1.7 seconds. It was supposed to be 3 seconds. If you were right in the middle line, which we're pretty close to, they said up to 3.3 seconds. So we only got half of our money's worth. And what's going on here? Well, if you remember pictures of asteroids like Eros, which is comparable in size, somewhat smaller, that's a dog bone. That's a really irregular shape. So something that's about twice as big as Eros, it could be an irregular shape asteroid. And when I talked to the experts, like the guy who actually did the calculation, and he knew about this particular asteroid. These are amazing people, because he had attempted to catch it in a previous occultation in 2017. 2 people tried to capture it. He failed, and the other observer saw it eclipse the star for 3 seconds. And he said, we talked about this and decided maybe this asteroid has an irregular shape. So if it were spherical and right on the eclipse line, you'd expect 3 seconds over and over again. But getting 1.7 seconds suggested to him that maybe we're discovering that this is an irregular shaped guy. Okay, so that's frame 42, 43, it's still on. 200, that's the end of my frames. It's still on. So it was out for 1.7 seconds. So it was a success. You can imagine how I felt having gone through the failure of not seeing it go out on the screen, and Larry and DR not seeing it go out in their telescopes. I got home and I'm clicking through this, expecting not to see anything happen, and whoop, it's gone. Whoop, it's back. For some reason, it's easier to photograph this effect than it is, just to see it in the screen. I don't know what's going on, why that is. All right, once you've observed it, then you submit your positive asteroid occultation report form, like a good member of IOTA. And they helped me with this because it has all sorts of jargon in it. I didn't know quite how to fill out, but you can see Tempe Allen University, they're getting their first report of occultation. And there's me talking about the technique used, 200.1 second frames. And so that told me nominally when the eclipse time was for disappearance, reappearance. There's an overall uncertainty in the amount that I'm not quite sure of. But the difference between those two, that 1.7 plus or minus 0.1 seconds, I think is reliable. So this was just a great thrill doing this and getting to know the people in the organization who, like I said, I think they have hopes for us in the future. Speaking of the future, Anybody like to volunteer? This one is not at 2 in the morning. This is the next one coming up. It's 1309 Hyperborea. Now, you get more time with this one. If you're right at the center of the eclipse line, it could be up to 11.6 seconds, it says in the top right. So this one, by occultation standards, it's just out forever, gone for a long time. And the midpoint of this eclipse is 10 p.m. Eastern time. How very civilized of this occultation. 10:02:52 Eastern. So we're going to be out there. Hopefully the equipment doesn't drop pieces on the concrete. And so we hope to submit our second, inshallah, as they say in Arabic, if Allah wills, our second successful observation of an occultation, the 5th of December. I managed to tell Noah the wrong date for the last one. So Noah, it's 5th of December in Eastern time, not universal time, 10 p.m. That'll be nice if you can come to. Oh, this time the star is more of a challenge. The star is 6 times fainter. It's 11.7 magnitude. But I've just been doing tests on stars of that brightness, and you can just make out a 100 millisecond frame of a star that's that much fainter. It's not easy. You have to stretch the exposure to actually see it, but it does work. And the other problem is that this time, tau isn't right in the center of the eclipse line. It's sort of 2/3 of the way to the edge. So it makes it exciting and dangerous. And because of that, maybe the total eclipse time will be 8 seconds instead of the best you could get, 12 seconds.
Why can the eclipse time be so long compared to the other?
Oh, it's just accidents. It's where the guy is in its orbit, moving, let's say, away from the Earth. If it's really moving away from the Earth, it's just in roughly the same position. And it's that kind of thing. This is longer than most of the predicted occultations by a fair amount. Usually they're 0.5 seconds, 1.5 seconds, numbers like that. And here's the other funny thing. Remember that chart showing Cetus, the sea monster, and Pisces? This is in almost the same location as the first one. It's not here, where the first one was. It's a little ways up. It says 1309 Hyperborea. And that green box is the size of the image I get. That's my full field with my SWO camera and my 190 millimeter Maksutov Newtonian telescope. And it helps to really sharpen up the focus carefully, because then you get all the light you possibly can into the smallest number of pixels. It brings it out. So that's the plan. Excuse me, that's hopefully going, if the weather cooperates. Oh, and also it's kind of cool. It's very close to Jupiter. Actually went out night before last and took some images of the field with the star there where Hyperborea is going to come and sit on it for a few seconds. And it's right close to Jupiter. That's the end. Thank you.